through school, I instead studied a different kind of transform. Oh, I forgot what it's called now. Omega transforms, which are a little bit different and dealt with a lot more complex numbers than this. So just to give some motivation or some idea behind Laplace transform, maybe I shouldn't have put the definition yet, but just to get the big picture of Laplace transforms. What are we doing in this class? Solving differential equations. I'm glad somebody answered something. I would have said, I don't know. I hope you guys know that we are solving differential equations. So we have a differential equation problem that we're solving. And where we are here is we can imagine ourselves in the t world. Let's just say it's called t world because we're doing stuff with respect to time. Okay, so we want to get to this goal of solving the differential equation. So the issue is sometimes all the stuff that we need to solve for this differential equation, calculus, is hard. Sometimes it gets kind of difficult. So what we want to do is we kind of want to break out of this world and go into another world. So welcome to the S world. It's related to T world in some sort of sense. And the way we're going to do things in the S world is we're going to use algebra. I say it's easy, but it's probably not so easy. But it is still algebra. Maybe. Yes, it's easier than the other way. And so in this S world, we're going to come up with an algebra problem. So what we're saying is that your differential equation is going to become an algebra problem, and then we'll do some easy algebra, easy in quotes, and then we're going to solve for it here. And then we're going to need to transfer back to the real world so that we can find whatever answer that we got in the S world. We're going to translate it back to the T world so that we can answer our problem back in terms of T. It's kind of like a substitution. Substitution, right? You're changing into different variables. You're going into a different world. It's kind of like the same thing. You're instead of saying that you're taking the integral with respect to x of some complicated thing, you do a u substitution, and then you change worlds, and now you're integrating with respect to u. That could be easier. And then you translate back to the x world. So the same thing. You start with a t world. You're going to exchange your differential equation to an algebra problem where you solve for s in the S world. And then you solve for it there, and then you need to translate it back into the T world to see what actual functions came up. And so this step going from our differential equation to the S world is called a Laplace transformation. So we're going to use Laplace transformation to go into the S world. We'll see that our equation will be an algebra equation that we should be able to solve. And then we're going to need to go back, and so we're going to need to find another process to go back, and we'll call that inverse Laplace. So that's the big picture. Okay? So that's the big picture. And what we'll do is we'll refer back to this big picture when we actually start solving for a differential equation, which we probably won't be able to do until Thursday, because we need to establish a handful of things first. We need to establish what it means to do a Laplace transform. We need to find Laplace transforms of some basic functions and basic operations and things like that. All right, good? All right, let's take a look. I'm going to recopy this definition. And I couldn't find the right font. This isn't really the L that we want. The L that we want is a script L. It looks like that. This is a scriptless L I can find in my font list. So the Laplace transform is usually written with this script L. And so this is a transformation for those people in linear algebra. This is a transformation that takes a function and transforms it into another function. You know, in linear algebra, we take vectors, transform it to another vector. This is a case where we have a function and we transform it to another function, which is an interesting transformation. And what we'll see later, without having to prove it, we'll see that this is actually, in fact, a linear transformation at that. And we'll talk about what linear transformation means. But nevertheless, this is a transformation. So what you do is you take your f function, this is the function that you're dealing with, that's your f, and then you put it into this operator, this transformation. This is an integral transformation that uses an integral to transform your function. And a couple of other things to note. We have we're integrating with respect to the variable t, but there's another variable s in there somewhere, right? So we're going to have to think about treating s as a constant and focus on just the variable t, and that's your variable of integration. Now, when you integrate over limits that are not variables, then you should have a constant. You will have a constant except for this s variable in here. So this will eventually become a function of s with a variable s. Have we seen something like this before? It wasn't exactly like this, but do you remember Green's function? You have g of x and t, and then you're putting in an integral, integrate with respect to t, and so you got some x that are constants that we can take out. So it's kind of similar, but not exactly similar, because this transformation goes from 0 to infinity. If you recall, when we take Green's function and we try to find the solution using Green's function, we integrate from x naught to x. So the variable is part of the limit. Here, the variable is not part of the limit. The limits are, I was going to say constant, but infinity, you can think of infinity as a constant. I know some people do. Anyways, so let's see if we can do some examples and see how these things transform. And it's nice to take simple functions like, what's a simple function? T? Let's start with t. Let's see where t goes. So according to this, there's some notation that we need to get used to here. your transformation will be saying you're going to take the Laplace transformation of the function t. And then it's going to pass through this integral transformation. So you need to integrate from 0 to infinity. You guys are comfortable with that, right? Improper integrals. Just put it into Wolfram alpha. So this is going to be e to the st. And I think the book calls it a kernel. This is your kernel function. Oh, negative. Thank you. That would make a difference. And then the function f itself. The function f is just t, so that'll be t, and then dt. And then we do this. I think this is an integration by parts type of deal. So let's do this by hand one time, and then the rest I'm just going to use Mathematica. So doing this by hand, we have, just so you get a feel for what happens to the s here. S is a constant, remember, e to the negative st. I would let u equal to the polynomial and v equal to e or dv, e to the negative st dt. And the antiderivative of this, if you have not just the t, but a negative s times t, negative 1 over s e to the negative st. So we continue on with this. U v, so that's minus 1 over s t e to the negative st minus the integral of v du, negative 1 over s. V is this, and du is just dt. Getting some Calc 2 flashbacks here. So we could just figure this out and then put the limits in. Minus 1 over s t e to the negative st minus, let's call that plus 1 over s. And then the antiderivative of e to the negative st is again negative 1 over s e to the negative st. And let's just do one quick simplifying and put this into, and then take the limits. So 1 over s t e to the negative st, and then a minus 1 over s squared e to the negative st. Now let's take the limit. Technically we put b in, and then you take the limit as b goes to infinity, right? I'll just put infinity, because we're all adults here. We can handle that. Okay? So let's put infinity in. Infinity comes first, and then minus, and then 0 in, right? So let's put infinity in here. Now I have t over e to the negative s over positive st now. And as you put infinity in here, is this going to go to infinity or going to go to 0? This is infinity over infinity, right? So if you do a quick L'Hopital's rule, then it'll be 1 over infinity, and that's going to go to 0. So that's one way to think about it. Another way to think about it is that this is a polynomial. This is an exponential. Exponential is going to go to infinity faster. So the denominator is going to go to infinity faster, and this is going to go to 0. Minus 1 over s squared times e to the negative st. And as t goes to infinity, this becomes e to the negative s, e to the negative infinity. What happens to e to the negative infinity? That goes to 0 as well. So the terms, when you put infinity in here, go to 0. Okay? That's done. Now let's put 0 in. We put 0 into the first term. The t is 0, so that whole thing is going to be 0. Minus 1 over s squared. What happens when you put 0 in for t? E to the 0. What's e to the 0? That's 1. So that is the only term that survives. So we got to make sure we got the sign correct here. This is a negative and a negative. So this will end up to be a positive 1 over s squared. Okay? So that is all Calc 2 stuff, right? And a lot of these, you got e to the negative st, and then whatever your f function is, if f is a polynomial or if it's a trig function, you're going to have to do some sort of integration by parts. If it's another exponential, we'll do an exponential example. We'll see what happens. It becomes a little bit easier. All right, so we get 1 over s squared. That is our transformation. So we have now successfully gone from the t world to the s world. And the s world, by notation, if we use little f for a function in the t world, we're going to use capital F for a function in the s world. If we use y, little y, in the t world, we're going to use capital Y in the f world. And that's just the notation. And your variable is now s. Did I say f world? I meant s world. So this is our transformation. Okay? Any questions? Is this okay? All right, so what we want to do is we want to find a bunch of transformations for a bunch of different functions, which we can run through and have Mathematica do, or we can just look at a table. If you look up a table of Laplace transforms on the internet, it's almost as popular as a table of integrals, and you'll see a list of these things. So this is one of them. Let's do another one just for fun. So suppose your f of t this time is e to the at. Okay? Let's do a Laplace transform on that. So our notation is the script L of e to the at. And this is an integral from 0 to infinity of the kernel, which is negative e to the st, times the function, which is e to the at. And for this one, we don't even have to use integration by parts or any fancy integrating, because we have the same base, e. We have e to the, now we can put this together, a minus s, factor out a t in the power. Yeah? Well, not given. It would be something that you would transform. So that's part of the problem, is that you're given a function that you're going to transform. So I don't know if that's what you mean by given. Yeah. It'll be in a question. Unless you get this and you have to go backwards. So there's a process for going backwards also. That would be the inverse Laplace going backwards. All right, so we were here, and a simple U substitution, or if people can do this in their head, just like we did the e to the negative st, the negative s comes down as the denominator of a constant. So 1 over a minus s, and then that's it. well, okay, the a minus s t, and we have to go from 0 to infinity. So what if I just say if you go from 0 to infinity, everything else is going to disappear, and then that's all you have left. So that is your transformation for e to the at. So your Laplace transformation we will call
Negative.
I think it'll come up positive. Maybe we should. Thought it was going to be easy, huh? Oh, this isn't how you do it. This is Mathematica. So e raised to the a minus s t bt. It's negative. Okay, fine. So this is going to be, if I just change the denominator, there'll be s minus a. So positive 1 over s minus a. Okay. All right. So that's the beginning of Laplace transforms. And we could do this for a bunch of different functions, but like I said, there are tables that exist already that have all this information. And here's a short one. So we didn't do the constant function 1, but apparently the constant function 1 turns out to be 1 over s. We did t to the first power. If you imagine n is equal to 1, you would get 1 over s squared like we got. We got e to the at. You guys just corrected me and made me write s minus a instead of a minus s. Thank you. And we got the sine and cosine functions are also represented here. They would have required that, the integral of e to the x sine x, that requires you to take the integration by parts twice and do some sort of weird subtraction. So we can not worry about that. The sinh and the cosh functions turns out to be, they're defined as exponential functions, so they're almost as easy as c here when we do the exponential function, except there's a pair of them. So if you work that out, you get another set of nice functions. So these are your Laplace transforms for the basic functions that we're going to deal with. I think if you can derive, let me highlight the ones that I think are important to derive. I think if you can derive this, the sine and the cosine, and this thing, if you can derive just, if you pick a specific number for n and then do the derivation for that. If you can derive the t to the n, that would be great. You'll see a pattern because it'll depend on how many times you do an integration by parts. And so however many times you're going to do an integration by parts, you'll see this n factorial kind of coming at you. I almost highlighted every one of them, huh? Well, the thing is that you just have to remember that function. There's that function that you need. So if you know what that integral is. I used to have to do an integral of from minus infinity to positive infinity, and that's the omega. Fourier, that's Fourier transform. That's what I remember doing. Anyways, so this goes from 0 to infinity. So just remember the formula for you to be able to derive any of these things requires that formula. So what is it? L of f is equal to the integral from 0 to infinity, and this is what they call the kernel times your f of t dt, and then your output is going to be, all the t's would be gone, your output would just be a function of s, and this is it. All right, let's see if we can find some interesting piece of information about Laplace transform. We'll see what it's good for later on, but as a transformation, people are often wondering if it's a linear transformation. And the idea of it being a linear transformation makes a lot of work easier for us. I guess we're not there yet. Not there. I thought it came sooner. Oh, here. Oh, I didn't write anything. That's why. What is the definition of a linear transformation? There's two things. What two things have to happen?
If you do it to the sum of something, then that's equivalent to if you do it to each and then add those.
Nice. Okay.
And then the other thing is that if you do it to a constant times t, then the same thing as if you multiply the constant times
Perfect. Exactly. So maybe I'll make a little bit of room here because I want to add a couple of things. So these should be properties that look familiar. In a sense that these are the same kind of ideas or same sort of properties that we took advantage of when we took derivatives and integrals of things, because the derivative and integral are both linear transformations. So basically, yeah, like Becca said, it's the Laplace of the sum is the sum of the Laplace transforms, and the Laplace of a constant times a function is a constant outside times the Laplace transform. So this gives us a way to deal with if we have a polynomial, if we have a sum of things, then we're allowed to use these rules because L, the Laplace transform, is a linear transformation. And that's always a nice thing. So we can continue, and really it would make sense because the Laplace transform is defined by an integral, and the integral is a linear transformation. So when we do the Laplace transform, we should see it as a linear transformation. So if we, for some reason, wanted to take the Laplace transform of e to the 2x plus t cubed, or plus 3t cubed, for example, this should be t. Then all we have to do is take the Laplace transform of them separately. And then we can get our answer. can even put the 3 out. So it's just on the previous page, and we just did it. Do you remember what the Laplace transform of e to the 2t is? It's 1 over s minus this a, which is 2, right? Plus, and then we have a 3 times, do you remember the Laplace transform of t squared? So it'll be, what's going to go on top? 3 factorial divided by s to the 4th power. Remember that it's s. All right, let me double check. Not that I don't trust you. So you can keep it like this, or you can rewrite it. 3 times 3 factorial. Okay? So this uses the fact that L is a linear transformation and allows us to find things like this. Let's go back. I want to make one more observation with all these Laplace transforms that we see. Anything you notice about the Laplace transforms, the functions on the other side? Asymptotes. S is in the bottom. There are a lot of S's in the bottom, right? And S is the variable that we're working on, right? So what we're going to be doing is we're going to be doing a lot of adding and subtracting a lot of those fractions with S's in the bottom. So when I say algebra is easy, we're going to have to do things like find common denominators. That shouldn't be too bad, right? We're also going to have to try to separate these fractions. What do we do? Separate fractions. What's it called? Partial fractions. So decomposing fractions. Now, partial fractions weren't really introduced to you as a student until you got to Calc 2, which makes you think this is like a calculus thing. There's no calculus involved in decomposing fractions. That's all algebra. Okay? So when I say algebra, I mean fractions and partial fractions. So that's the kind of algebra that you're going to have to deal with. That's in place of doing all kinds of weird integrals and derivatives and calculus stuff. That's what happens when we go to the S world. All right. So they have a couple of other definitions and theorems that are for theory's sake. I think they're kind of important, but I don't know if I'll stress them too much. But the question comes up, when do we get to use the Laplace transform? What kind of functions? I mean, we've dealt with nice functions. We've got t, we've got the exponentials and trig functions, and even hyperbolic functions are nice functions. So when do we get to use? And sometimes when we're dealing with differential equations, we start using piecewise functions as well. So can we use it on piecewise functions? Can we use it on what kind of functions? So they define a piecewise continuous function, but that's like the pre-calculus stuff. And so a piecewise continuous function means it's continuous in pieces, as long as, so you can have something that's even not continuous as long as the pieces that are here are continuous, and then that's an okay type of function to deal with. A function f is said to be x of exponential order if there exists a constant c and m, and another parameter t, such that the maximum value for f, the maximum absolute value for f, is going to be contained, or it's going to be within this expression. So m and c are constants, and then t is going to be at some point in time that you can start this inequality. Okay. Let's see if we can come up. So they have some interesting, good examples in the book. And so let's say this is your f of t. Let's do your f of t in blue. And it could be piecewise or whatever. And what they're saying is that after there's going to exist a function, constants m and c, that you can put into a function, an exponential function. So let's say m was here, and c just tells you how steep this is supposed to be. So that after a certain point, capital T, your function that you're dealing with is going to be less than that exponential function that they have. So that's all it's saying. And what they don't want you to have here is a function that's just going to keep going exponentially higher and higher and would grow exponentially faster than any exponential function that you can think of. Not exponentially higher, but that would go higher than any exponential function that you can think of. So if you had an exponential function, and if your graph eventually passes over it, then it's not of exponential order anymore. Like something like this. This is your f of t. And if f of t grows faster than any exponential function, then that's not permitted. Then we don't have a Laplace transform for it. Can anybody think of a function that goes faster than that? Not very many. Let me introduce you. Uh-oh, we're going on a tangent. E to the t squared? Yeah, that's a good one. I didn't think about that one. Have you guys heard of the gamma function? Sounds cool, huh? What do you know about the gamma function? It's that function that the Incredible Hulk was playing with when he got all radiated. No. There's some gamma rays and all that stuff. Gamma function, anybody know what it is? So the gamma function is a special function. The gamma function is the factorial function for numbers that are not integers. Now, when you think of 5 factorial is 5 times 4 times 3 times 2 times 1. All good, right? And when you think of 10 factorial, you do the same thing. But what if you say, what is 1/2 factorial? What's that? Or 0. What is 0 factorial? 1. Why is it 1? Because of the gamma function. When I was in, yeah, I told you that story. when I was in school, I was fascinated by this factorial. What's 0 factorial? How does 0 factorial equal to 1? So I asked this really smart physics guy. I said, hey, how come 0 factorial is equal to 1? Otherwise, the gamma function won't work. I said, okay. And so I drank some more beer.
Wait, what?
What? Anyways, the gamma function for positive integers is defined to be the factorial, and for other numbers that are not integers is defined to be this indefinite integral. Now, we were just talking about transformation. This looks awfully lot like our whatchamacallit? Laplace, yeah. This looks a lot like Laplace. So this is not quite Laplace transform because you're not taking a function and moving it into a function, right? So your input here is a number and your output is going to be another number with an x in it. Maybe it's not a number. Maybe it's a function. Anyways, so what you have here is something that's different from a regular transform. But this is like the function x factorial. And then if you notice the graph, it's not defined for negative integers because weird things happen with negative integers. They go off to infinity. But it is defined for numbers like 1/2. So if you have a 1/2 factorial, whatever that means, that can get translated into a gamma function. Is it? It's supposed to be 1. Does it say not defined for 0? Oh, here it goes.
Well, maybe it's how you said. Yeah.
Oh yeah, so it's not defined for the. So that's the other thing is the gamma function. The way the gamma function works, there's like a shift to it. I kind of know it as n factorial. Okay, we're really off on a tangent here. So the gamma function, the way I see it is usually I look at it as gamma of n plus 1 is equal to n factorial, and that's how I relate it. So when they say the gamma function is not defined for 0 when n is equal to 0, you have gamma of 0 is equal to negative 1 factorial, and so that's not defined here. So if you want 0 in the factorial, you would need to put n is equal to 1. So somebody said that, right? Okay, so that was correct. And so if you put n is equal to 1 into this integral here, this is going to be equivalent to computing 0 factorial, and this is the integral from 0 to infinity of x. Oh, x is equal, no, n. Oh, oh they wrote this wrong. No, it's right. X to the 0, e to the negative x dx. And so if you do this, this is equal to 1. And that's what 0 factorial is. Okay, that's the gamma function. And so that would be possibly one of those functions that are not, what were we talking about? Of exponential order.
Why not?
Because they shoot up too fast, and you can't have an exponential function that contains it. It's always going to go higher. Okay. Anyways, I squeezed in the gamma function because it's in here HBA. So it wasn't just a tangent. It was kind of an important tangent. It's also embedded in the Bessel functions that you guys are going to be working on. So beyond that, I think when I asked for some information or what you guys thought about the Laplace transforms that we found so far, Becca mentioned something like, yeah, they all look like they're approaching 0. So all your, if we just collect a handful of the ones I remember off the top of my head, they kind of look like 1 over s, or 1 over s minus a, or s over s squared minus k squared, or something like that. A bunch of these things. If you take the limit as s goes to infinity for all these things are all going to approach 0. Because your denominator is going to dominate with that variable over the numerator. So again, getting you ready for dealing with a lot of fractions, common denominators, and partial fractions, and things like that. That's what we're going to deal with. Okay. All right. So inverse transformation. So we're going to go into the S world, and we're going to mess around with stuff in the S world, and we have to be able to jump back. So an inverse transformation would be a way to take it back. And a lot of times, I didn't write the formula down. I should have started off with a formula. Let me see if I can find the formula real quick. I have the book open. Doesn't say in the book. You just have to do another integral to go back. Crap, sorry. There's got to be a formula for it. Yeah, it's this business. Oh, maybe that's why there's no formula for it in the book. All right. I think it's worth taking a look at this. So we go to the S world by doing a Laplace transform, and then we do the work we're going to do in algebra, and then we need to go back to the real world. So what we need to do is we need some sort of inverse Laplace transformation. And so the inverse Laplace transformation turns out to be this complicated looking thing. Yeah, and it starts to include complex numbers, right? Which shouldn't have complex numbers, but if you do the calculation here, you see the complex numbers will disappear. So instead of trying to find some complicated formula, I'll just say this is too complex. Get it? Let's just say instead of dealing with that formula, what we're going to want to do is whatever expressions we have in our algebra world, in our S world, we're going to want to somehow rewrite it and make it look like one of these functions. Okay, because these are the functions that we can take back from the S world back to the T world. So in other words, if we remember that big picture where we have the dE, the differential equation, and then we go into the S world. And then let's say in the S world, we come over here, and then we come up with 1 over S squared minus 2S as our solution. Now, if I take this, I want to pull it back into the T world. I look at this expression, this function, and I don't see it anywhere here. Oh, I guess it's here. Oh, I don't have a K, right? On top. So for that's an easy fix, actually. I was thinking of something more complicated. But let's just say...
But you've got 2S on the bottom, not K.
Oh, okay. Okay, so good. This is what I wanted. So this is not in my list that I'm able to take back. So what are you going to have to do? This is where you're going to have to split this up. Now, ideally, you would use, if we had a nice transformation back, we can use one of these formulas to just transform back. But because that's too complicated, we're going to try to rely on a set of S functions that we can transform back. This, unfortunately, does not fall into one of them. I thought this was a 5. Now, because it looks like this, what you're going to have to do is you're going to have to, let's see, maybe factor out an S. And then do some partial fractions. I don't know this off the top of my head, so I'll just put A and B. And because the transformation was a linear transformation, these things can be treated separately. So I have my A over S as just being this thing. So back into this is my F of S. So back into the real world, I'm going to get A times the transform of 1 over S is 1 plus B times the transform of 1 over S minus 2 is e to the 2s. 2s or negative 2s? Positive 2s. Or not s, but t. I guess maybe I should take an extra step here. So we're able to take advantage of the linear transformation not only going from the T world to the S world, but also going from the S world back to the T world. So because because the Laplace transformation is a linear transformation, the inverse Laplace will also be a linear transformation, and this is what we have. Okay, so this would allow us to go back. Any questions? From Wikipedia. This is just another way to go from, if you know what your F is, your Fs, this is a way to come back and get your original F of t, little f of t. So you have Fs something, a function in the S world that you messed around with, and you want to go back to the T world, this would be the integral to do it. This would be one of the ways to get there. What's gamma? Anyways. Oh, look, their Laplace transform L is the same as mine. It's still not the right one. In all the books, it's always that script L. Okay. So we're dealing with differential equations, and our equations are not just going to be equations with t's, e to the t's, and sine t's, and things like that. Our equations will have derivatives, right? Because it's a differential equation. So what we need is a transformation of a derivative. And so we have the formula for that. So I'll put this formula down, and we'll examine it to find derivatives of things. And right now, all these things are coming to you at different pieces. And then, like I said, next time we'll actually see if we can put everything together where we're actually going to be able to solve a differential equation that we might know the answer to, or maybe might not know the answer to, but we'll use Laplace to be able to solve for it. Okay. So we're looking at functions and their derivatives to be continuous and of exponential order. So again, the exponential order business just says that this is going to be something that we can take the Laplace transforms of. And we're not going to be dealing with other weird functions that are not of exponential order. And the Laplace transform of the nth derivative is going to be equal to this. Okay? Okay. So let's see if we can actually simplify this in terms of things that we would actually be able to deal with. So we know that the Laplace transform of little f of t is equal to capital F of s. So let's see if we can find the Laplace transform of the first derivative by using this complicated looking definition. So n in this case is what? 1. So it looks like this will be s to the first power, capital F of s, minus it'll be what? S to the 0 or 1 times f of 0. What's f of 0? It's the original function evaluated at 0. I guess. What's f of 0? Let me ask again and see if anybody comes up with a different answer. It's a constant. That's what I wanted to do. F of 0 is just a constant, right? So it's not a function anymore. So this is our differential equation. Or, I'm sorry, this is our transform of our first derivative. No. Well, first of all, x. You mean x is an independent variable x, right? Like y of x, x. Well, no, because you have to decide from the beginning whether you're going to want your independent variable to be x or t, and we're just going to assume that we're going to be in t. And so that's the other thing, is that just by notation and just by notation, we're going to assume that your t is your independent variable, not x. All right, so if we do a couple more, maybe try to get us ready for finding the first and second derivatives and stuff like that. This would be n is equal to 2 minus, when n is equal to 2, we have s, f of 0, minus s, n is equal to 2, so 2 minus 2 is 0, and this is just f prime of 0. Now, I guess this would be better seen in terms of the way we write our differential equation, right? We write our differential equation with y's, so maybe if we write it as y double prime, this might be a little bit more palatable for us. This is s squared, y, capital Y of s minus s times y of 0 minus y prime of 0. So these linear transformations, when we consider the derivatives in a differential equation, we're actually also going to include the initial conditions as well. And usually we want our initial conditions to be off of 0. Okay? So what we're going to do is we're going to take a differential equation, we'll transform the whole differential equation, and then we'll see if we can inverse transform it back. And we'll compare it to differential equations that we've already solved and we know the answers to, and then we'll jump into some differential equations where we don't know the answers to. All right.